In this video, we'll work on some homework solutions for Appendix G, integration involving partial fractions. Now, problems 1 through 6 in the homework ask us just to set up, but do not solve, do not calculate the values of the numerators in our partial fractions. So those are just set up, but do not solve problems. So I'm not going to do any of the problems from 1 through 6 that are in the assignment. But I will start with, if we take a look, we can start with problem 12, right? That's our first actual integral. Problem 12 is the integral from 0 to 1. We have x minus 1 over x squared plus 3x plus 2 dx. We take a look at this. Remember, our first responsibility is to determine what type of solution strategy are we going to employ. Are we going to use integration by parts, for example? Are we going to do a trig sub? Are we going to do a trig integral? Or are we going to try partial fractions? Maybe it's just a straight antiderivative. Maybe it's a u sub. So our first job when we get a problem is to take a look and go through our checklist and see what we think we will employ as our problem solving strategy. These problems come from the section about partial fractions. So that's our assumption, but it never hurts to just take a second, run through the other opportunities for solutions, methodologies, and determine if they're applicable. Once we decide it's partial fractions, we want to make sure the degree of the numerator is smaller than the degree of the denominator. If it's an improper fraction, right, we begin we begin by doing polynomial long division. We don't have that here. Our numerator has a degree of 1, our denominator has a degree of 2. So we're just going to go to our very next step. Our very next step then is to factor, if possible, the denominator. So this would be the integral from 0 to 1. We would have x minus 1 divided by, and this is going to be x plus 2 times x plus 1, when we factor x squared plus 3x plus 2. And then we look at this and we ask ourselves, which of our 4 cases am I going to employ to solve this problem? This is case 1. We have a linear factor and a linear factor, and they are distinct. So this is a case 1 partial fraction. We said that to solve this, we're going to rewrite this as the integral from 0 to 1, and we're going to write this as a over x plus 2 plus b over x plus 1 dx. All right, this is our partial fraction strategy. Now I'm going to drop the integration for now. I'm going to just do the partial fraction work, and we'll come back and we'll plug it into the integral at the end. So where do we go from here? Right now we have this. If we just rewrite our partial fraction, remembering that since these are linear factors in the denominator, since they're linear, then the numerator is going to be a constant. We use A, B, C, our capital letters typically to represent these constants. This is linear, so this is a constant. This is degree 1, so this is going to be degree 0. Now, from here, we could get a common denominator over here on the right-hand side. And if we did that, we would end up with x minus 1 over x plus 2 times x plus 1 is equal to a times x plus 1 plus b times x plus 2 divided by x plus 2 times x plus 1. Now, in mathematics, we call this an identity, right? That's what we say. We say this statement right here, we say that is an identity. Now, what do we mean by calling it an identity? We mean that is true for every value of x. Every value of x. Now, our problem-solving methodology says, all right, we're going to rewrite just the numerators. And now we have a couple of choices on how we proceed. We could multiply these out and use a system of equations to solve for A and B. That is acceptable. In a case such as this, it might be a little more straightforward. My pen's leaking a little ink here. It might be a little more straightforward instead of using a system of equations just to decide. My pen is hemorrhaging ink. Not really sure what's going on. We're going to take this pen and retire it. There's a new brown pen. So we're going to say let x equal -1. Now I'm picking -1 because when I plug -1 in here for x, -1 plus 1 is going to be 0. So I'm picking -1 because it is a 0 of one of my two denominators. Okay, it's not an arbitrary choice. If I put -1 here, I would get -1 minus 1. That's going to give me -2. If I put -1 here, that's going to be a times 0. So that's gone. And if I put -1 here, that's going to be b times 1. That simplifies then to -2 equals b. Now I'm going to double underline that because we have found the value for b. We have found the value that's going to go right here when we go back and solve our integral. Now, to find the value for a, I'm going to pick the 0 for this. And so I'm going to let x equal -2. If x is -2, -2 minus 1 is going to be -3 on the left-hand side. -2 plus 1. All right, and x is -2. -2 plus 1 is -1. So that's going to be a times -1. -2 plus 2 is going to be 0. So that's going to be b times 0. That's gone. If I solve this, I get 3, and negative divided by negative makes a positive, equals a. And so now we're prepared to go back and rewrite our integral. Our integral is now the integral from 0 to 1. A we determined was 3, so that's going to be 3 divided by x plus 2 plus b we decided was -2, so we'll change our plus to a minus. 2 divided by x plus 1 dx. And these integrals are the u substitutions of the natural log. Here we would let u be x plus 2. Here we would let u be x plus 1. I'm not going to go through those steps. You can work them out in detail on your paper. So we would end up with, this would give us 3 times the natural log of x plus 2 minus 2 times the natural log of x plus 1. And we want to evaluate this between 0 and 1 because problem 12 is a definite integral. When we input a 1 in here, we're going to have 3 ln of 3. We don't need the absolute value because 3 is positive. When we put a 1 in here, we're going to have minus 2 ln of 2. Now we have, by the evaluation theorem or the fundamental theorem of calculus, whichever way your book puts it out there, we're going to plug a 0 in here and we're going to have 3 ln of 2 minus 2 ln of 1. Now, the natural log of 1 is 0, right? The graph of the natural log goes like this. So the natural log of 1 is 0. And so this goes away. We have 3 ln of 3 minus 2 ln of 2. And here we have minus 3 ln of 2. So that would give us 3 ln of 3 minus 5 ln of 2. Now, the answer may be expressed in this manner in the back of the book, or we could use the log property that says if you have a log base b of r, that a can go up here and we can rewrite that as log base b of r to the a. In other words, we can put this 3 up here. This is going to be then the natural log of 3 cubed, or the natural log of 27, minus here we're going to have the natural log of 2 to the 5th. And so we could express this as the natural log of 27 minus the natural log of 32. Not sure which way it's expressed in the book, but it's one of, I would be fine with this on an assessment. I would also be fine with this. So that's problem 12. Okay. I'll pause the recording while I erase, and we'll get back here with another example. All right, for my next example, we'll look at problem 23. Problem 23 says we want to integrate 10 divided by and we have x minus 1 times x squared plus 9. X minus 1 times x squared plus 9 dx. Now, this is an indefinite integral, so we're not going to have to evaluate it. That's nice. We're going to have to remember to add our constant c at the end. So when we take a look at this, we have to ask ourselves, which case are we working with here? Case 1, case 2, case 3, case 4. This is linear. It's not repeated. This is an irreducible quadratic. We can't reduce x squared plus 9. So that means we're going to rewrite this as the integral. We're going to go ahead and move that 10 out front. We'll just get that out of the way right now. And we're going to rewrite this as a, because this is a linear term. So that's going to be a constant. That's a over x minus 1 plus, this is going to be bx plus c, because remember, if this is an irreducible quadratic, then we have to have a linear term in our numerator. So bx plus c. So this is where we would begin, right? Now, how are we going to get this to work? What are we going to do here, right? All right. So looking at what we have here, I'm not really sure what I was thinking by putting this 10 here. That 10 doesn't go there. This is my partial fractions approach. 10 is going to be on my left-hand side. So our numerator over here is 10. Here, when we get a common denominator, remember our numerator is going to be a times x squared plus 9. Right? We're getting a common denominator plus bx plus c times x minus 1. Okay. Now, we can adapt our let x equal approach here, because if we let x equal 1, this is going to give us 0, and 0 times bx plus c, the b and the c are both going to disappear. So if I let x be 1, there are no x's on the left-hand side, so that's a constant, that's 10. If I let x be 1 here, I'm going to get my a 1 squared is 1 plus 9, that's going to be 10. And if I simplify this, right, if I simplify this, I'm going to get a equals 1. Now, we know a is 1, right? A is 1. There's no doubt about that. Why is that important? Well, we can take this, remember, this is our identity here. We can take our identity and now we can rewrite it because we know a is 1. Now, I'm not going to choose another value for x. There is no value for x that I can put in here and cause this to be 0. X squared plus 9 is an irreducible quadratic. It has no zeros. That's a parabola that's moved up 9. It opens up. If we were to draw the graph of that parabola, it goes like this. It has no zeros. So this was the only factor that had a 0. So we used it. And with that, we were able to establish that a was 1. Now I'm going to go back and I'm going to rewrite this. This is now going to say 10 is equal to, a is 1. So this is going to be x squared plus 9 when I multiply it by 1 plus a is 1. There's no a's over here. So here we're just going to have our bx plus c times x minus 1. This 9 can move over here. So if we rewrite this identity, this 9 can come here. It'll be negative. We'll get 1 equals, we'll have x squared. Now we're going to go ahead and FOIL this out. So we're going to have plus bx squared, right? Bx times x plus cx. And then bx times negative 1 minus bx, and then c times negative 1 minus c. Okay. Now we have to solve for b and c. We're going to take a look. We're going to use our sort of a pseudo system of equations approach here. We have an x squared here and an x squared here. There are no x squareds on the left-hand side. So we know 0 is equal to 1x squared plus bx squared. So that gives us, just looking at the coefficients, over here there is the coefficient of the x squared term is 0 because it's not present. So here the coefficient is 1 and here the coefficient is b. Now that gives us the equation, if we solve that, b equals negative 1. So now we have been able to find our value for a and our value for b. Now, if we take a look at our constants, I'm going to choose the constants. The only constant here is minus c. On the left-hand side, we do have a constant. We have 1. So this says 1, the constant on the left-hand side, has to match the constants on the right-hand side, of which there's only minus c. That tells us that c is equal to, when I move the negative over, negative 1. So we don't have to set up a formal system of equations to solve these problems. You can, but sometimes you can just work with the coefficients, set up the equations, and sometimes you can get lucky enough to be able to find the values without having to set up a formal system of equations. Now, if you're concerned, right, if you're concerned, and you're wondering, did I get it right? Did I get it wrong? There is no x over here. On the left-hand side, there's no x term. So we could set up another equation. We could say, if we're looking at the x's, there are none on the left-hand side. On the right-hand side, there's a cx minus a bx. And then we could take our values for c, put it here, negative 1. Put our value for b here, negative. So that would be negative 1 minus minus 1. That does indeed equal 0. So that kind of, it's not a full check. We weren't able to check the value of a, but it does confirm for us that our values for b and c do make sense. Now from here, from here, we're going to go back to our integral. So going all the way back to our integral is now the integral. A we decided was 1, so that's going to be 1 divided by x minus 1, plus we decided B and C were both -1. This is going to be a -1 here, and this is going to be a -1 here. So I'm going to factor out the negative sign. And then B is going to be 1, so that's going to be x. It's +1 now because we factored the negative out. C is also going to be 1 because we factored the negative out. And we have x squared plus 9 dx. Now we have to integrate this. Okay. When you get an integral of this type here, we know this integral. We did this in the last example. This integral is the natural log of the absolute value of x minus 1. Over here, however, though, we have to do a little more thinking. Okay. So if we just rewrite this as 3 integrals, and I say 3 integrals because I'm going to break this up. I'm going to make this x over x squared plus 9, negative sign right from here, minus, and I'm going to use the 1. Oh, I forgot my dx, didn't I? Let's put that in there. I'm going to have my 1 over x squared plus 9 dx. So the trick with an integral like this, where you have an irreducible quadratic on the bottom, is to split it into 2 integrals. This integral we can do by inspection, right? By inspection, we know this integral is equal to the natural log of the absolute value of x minus 1. This integral we can do by inspection. This is inverse tangent. This is 1 over x squared plus 3 squared, right? That integral is the integral of 1 over x squared plus 3 squared dx. That's one of our integration formulas from back in Calc 1. This is equal to minus 1/3 inverse tangent of x over 3. Now that just leaves us the middle integral, and that one we're going to do with a u substitution. We're going to say u equals x squared plus 9 du equals 2x dx. And we're going to look at the numerator. We're going to say I need a 2 here. Hence, I have to put a half there. So when we integrate this, we're going to get minus 1/2 the integral. The numerator is du, right? Du 2x dx. The denominator is u, x squared plus 9. Well, that's another natural log. So our final answer then is going to be our natural log of the absolute value of x minus 1 minus 1/2 the natural log of u, which in this case is going to be x squared plus 9 minus 1/3 inverse tangent of x divided by 3. Now, there's one final thing I want to call your attention to in the presentation of this answer. Please notice that this is the natural log, and this is a parenthesis and a parenthesis. That is not an absolute value. I see that this is du divided by u, and the answer to that is, when you integrate, the natural log of the absolute value of u. However, our u is x squared plus 9, and as we pointed out, x squared plus 9 is greater than 0 always. Here's the graph. Since it's greater than 0 always, it makes no sense to specify that we need the absolute value of that. It's never negative, so we do not need to take the absolute value of it to force it to be positive. So we don't want to express answers with absolute value signs when they're redundant. We want to make sure that we write our answers down without the redundancy of the absolute value sign when it's not necessary. Okay, when it is necessary, like in the case of x minus 1, I don't know if that's positive. I don't know if that's negative. If x is -7, then that's -8. I need an absolute value sign. But if x is 22, this is 21. I don't need an absolute value sign. Since I don't know my value of x, I can't tell if that's positive or negative, and thus I need the absolute value sign. Here, this is always positive, right? We know this is always positive. We can see it's always positive. All right, that's number 23. I'll turn off the recording and come back to you once I get this erased. All right. For my final problem on this video for partial fractions, we'll take a look at the homework. We'll take a look at number 28. Okay, we'll skip down to 28. 28 is the integral from 0 to 1, another definite integral. We have x divided by, and our denominator on number 28 is x squared plus 4x plus 13. Now, x squared plus 4x plus 13 is an irreducible quadratic. Remember, the way we can determine if this is an irreducible quadratic is we can go look at the discriminant, b squared minus 4ac. And if our discriminant is negative, then this is irreducible. And here in this case, we have b is 4, so we have 4 squared minus 4 times a, which is 1, times c, which is 13. 4 squared is 16 minus 4 times 13 is 52. That's less than 0. So this is irreducible. It doesn't repeat. So we're in case 3. So we're going to rewrite this as the integral from 0 to 1. And we're going to rewrite this as ax plus b divided by x squared plus 4x plus 13 dx. And now it's our job to go find a and b, right? Okay, so if we look at this problem in our traditional sense, we think to ourselves, okay, this is irreducible, it's a quadratic. This is my approach. So then our next step, of course, is to set up our identity. Now we don't have any common denominator. Both these are the same denominator. So we end up with x equals ax plus b. And then if we do our work, right, there's 1 here. So this is an x, this is an x. That gives us a equals 1. And from there, we can see that b equals 0. Now, if we do that and plug those in right here, 1 for a, 0 for b, if we do that, we end up with 1 for a, 0 for b. Or we end up with this. We end up right back where we started. We have the same problem on the right, same problem on the left. Partial fractions didn't help us at all here. So when we get a situation like this, right, there's an adaptation. I would even call it an adaptation. There's just another way to solve this problem. And that is, we have to think about completing the square on the denominator. Okay, so we didn't see this in the notes. Actually, we did see this in the notes, but I didn't make a big deal out of it, but I'll make a bigger deal out of it here. We have a lot more time to go over it. We're going to complete the square in the denominator. We're going to take our x squared plus 4x plus 13, and we're going to rewrite it like this. X squared plus 4x. Now, b here, back to our algebra 2 days or algebra 1 days, b is 4. Then you take b divided by 2, that's going to be 2. And then you take b divided by 2 and you square it, that's going to be 4. So we want a 4 right here. Now we have 13. So when we use up 4 of the 13, that leaves us a 9. And when we rewrite this, this is x plus 2 squared plus 9, or this turns into x plus 2 squared plus 3 squared. And now we should have bells and whistles going off in our heads saying to ourselves, hey, I think this is going to turn out to be an inverse tangent. We have somebody squared plus somebody squared, right? It wasn't a coincidence when they wrote this problem in the book that when we needed a 4, there was a perfect square 9 left over. Now, this does not have to be a perfect square, right? If this was a 7, we would have this written as x plus 2 quantity squared plus root 7 squared. But your author was being nice. They made it 4 away from 13, 9. So we're going to rewrite this integral like this. Integral from 0 to 1, x divided by x plus 2 squared plus 3 squared dx. And we're going to think to ourselves, maybe this is an inverse tangent problem, right? Maybe it's inverse tangent. The trouble with that is we're not allowed to have a numerator of x if this is just a straight antiderivative for inverse tangent. So while it looks like inverse tangent, and inverse tangent is going to show up down the road, right now we just have to put our thinking cap back on and make another swing at this pitch. So we think to ourselves, well, I feel like there should be an inverse tangent here. But right now, inverse tangent is not jumping out of this because I have an x in the numerator. When all else fails, let's just see what happens if we try u sub. If I let u be x plus 2 quantity squared plus 9, and we take the derivative of that, down chain rule, down comes the 2, x plus 2 to the first, the derivative of x is 1, the derivative of 9 is 0, here's my dx. We would need, right, if we were going to make this work as a u sub, we would need on the top a 2x plus 4 dx. We don't have that, but we can make that show up, right? We can make that show up. We can put, instead of an x up there, we can put a 2 times x plus 2 and a minus 4. Now let's think about what that is. That's a 2 times x plus 2 minus a 4. Sorry about that, my dog started barking. So we have a 2 times x plus 2 minus 4. Now what have we really done? We've got a 2x, we have a plus 4, and we have a minus 4. So we haven't really done anything. All we've done is multiplied the x by 2, right? We've multiplied the x by 2. Because when we simplify this, this equals 2x. If we've multiplied the x by 2, we need to put a 1/2 out in front. That's how we do u subs. Now take a look at what we have, right? We have now 1/2 the integral from 0 to 1, 2 times x plus 2 dx divided by x plus 2 squared plus 3 squared. That's right here. That's our u sub. Minus, we still have to write the integral down that goes with the 4. 1/2 the integral 4 divided by x plus 2 squared plus 3 squared dx. So when we can't find a partial fraction solution to work, when the partial fraction turns us right back into the regular problem, what we do here is we complete the square. Okay, we complete the square. Then we look to see what our u sub would require us to have. We needed a 2x plus 4. That's what we needed, a 2 times x plus 2, which really was 2x plus 4. So I put a 2x plus 4 up there and then just tacked on a minus 4. Now we said back when we were in section 5.5, if you're going to multiply by 2, you have to divide by a half. So we did. Now, if we take a look, right, if we take a look at what's written on the whiteboard right now, our u is x plus 2 squared plus 9. That's right there. Our du is 2 times x plus 2 dx. That's right there. This integral is 1/2. No bounds. Remember, when we use a u sub, we don't put down these bounds or x's. Du divided by u. All that work, and it turned out to be one of our favorite integrals. Over here, we have minus. I can bring the 4 outside, right? So that's going to be 2. We're going to have the integral of 1 divided by x plus 2 squared plus 3 squared dx. That's our friend inverse tangent, right? That's our friend inverse tangent. That is the integral of 1 over something squared plus a constant squared dx, which we said was 1 over a inverse tangent of x over a plus c. Now here, in this case, right, in this case, we do have our bounds 0 to 1 because we haven't done a u sub here. We're still working in x. So what does this turn out to be? This is 1/2 the natural log, the absolute value of u. Our u is here it is. It's right here, right? It's right up here. It's purple. It's right there. We know what that is, right? We know what that is. If we expand that, we have it right here, right? We did the expansion right here. That's going to be x squared plus 4x plus 13. Now that is an irreducible quadratic. It's always positive. So we don't need the absolute value signs. Plus, remember, we're going to evaluate that between 0 and 1, right? 0 to 1. This integral right here, this integral is our friend inverse tangent. Minus 2. And it turns out to be 1 over 3. Our a is 3. So 1 over 3 puts a 3 down there. Inverse tangent of our x. In our case, our x is x plus 2, right? That's what we have squared. So that's going to be x plus 2 divided by 3. And we're going to evaluate that between 0 and 1. Now, that's a handful, right? I mean, that's a lot going on. You can back the video up, watch it 4 or 5 times, listen to my explanation every time. Sooner or later, it's going to make sense. Watch it enough, it's going to make sense. If it doesn't make sense after watching it once, and just back it up. Now, we still have to evaluate this, right? So if we evaluate this, what are we going to get? Well, here we're going to get 1/2 the natural log. We're going to put a 1 in here, right? So that's going to be 1 plus 4 plus 13. That's going to be the natural log of 18. Minus 1/2. We're going to put a 0 in here. So that's going to be the natural log of 0 plus 0 plus 13. Now, We were taught in pre-calc, if you have the natural log of A minus the natural log of B, that's equal to the natural log of A divided by B. That was a property of logs we were taught in pre-calc and algebra 2. So I can simplify this as 1/2 the natural log of 18 divided by 13. Okay, that's an expected outcome for a Calc 2 student. A Calc 2 student shouldn't leave something that looks like this. They should express it like this. Now, what's going on over here? Well, we have minus. We have 2/3. When I put a 1 in here, right? When I put a 1 here, I get 1 plus 2. That's 3 divided by 3. That's inverse tangent of 1. Inverse tangent of 1 is pi over 4. We're supposed to know that, right? We're supposed to know that. What angle has a tangent that's equal to 1? And the answer, that's pi over 4. That's just supposed to be one of those things we know, like we know, sine squared plus cosine squared equals 1. We're just supposed to know that. At this stage of our education, that's supposed to be something we're aware of. Minus. When we plug a 0 in here, we get inverse tangent of 2/3. Now, I don't know what the inverse tangent of 2/3 is, so I can't really simplify that. So I can take the negative 2/3 times this, right? That gives me 12 over 2. That gives me minus pi over 6. And then 2 negatives make a positive, plus inverse tangent of 2/3. I don't know what angle has a tangent that equals 2/3. That's not one of my special angles, so I'm not supposed to know that. I'm not expected to come up with, I don't have a calculator. We're not going to be allowed a calculator on any assessment. So if you were to express this with some kind of decimal, it would make me very suspicious as to how you knew the inverse tangent of 2/3 off the top of your head without using a calculator. All right, so I've worked on problems 12, 23, and 28. Specifically, I did 28 because it's one of these, it's a special case, right? It's not impossible, but the algebra is a bit hairy. And so rewind the video, watch this problem over and over and over until you can make it make sense. All right, I hope this helps. I'll see you all during our next class.